Welcome, everybody. It's my pleasure to introduce Chunyin, who will be telling us about the topology of preferential attachment.
Thank you very much for coming, and thank you very much for having me. Special thanks to ATR and directors and Henry for the invitation. Before I start, I want to talk about two things first. First of all, it's the first time I give a purely Zoom talk, and I would really appreciate it if you could turn on your camera so that I can see some human faces. That would be very helpful to calm my very nervous soul right now. So that would be very helpful. Thank you so much. Nice to see more faces. And the second thing is an advertisement. I'm going to graduate next summer and I'm looking for a postdoc. So if you're hiring, please do not hesitate to let me know. Okay, with these two things out of the way, I can finally start my talk proper. I'm going to talk about the topology of preferential attachment. People here generally love topology, and I'll explain why we care about preferential attachment. So preferential attachment is a random graph process that produces graphs that look like this. So what is this picture? It is a snapshot of the internet back in the early 2000s. Each node is a web page, and each edge is a hyperlink. So from a topological perspective, this is a graph, and hence it's just a bullet of circle, not very interesting. But if you look at this picture more closely, you seem to see like there's a dense core of nodes at the center and some like sparser nodes at the periphery. So maybe there are more structures to just a bullet of circles. Okay, so that's the first question. We want to understand, we want to have some sort of topological description that's more than just a bullet of circle. And this is important because preferential attachment mechanisms tend to produce graphs like this, graphs with a dense core of well-connected hubs and some very sparse nodes that are much less well-connected. And it's a very useful model for many systems like the internet or social systems and many biological systems as well. One thing to notice is that the preferential attachment mechanism is random. The internet is random. For example, if I update my web page after this talk, it's going to change a little bit, not by too much, but it's going to change by a little bit. Okay. So whatever conclusion you want to draw about this object, you want to be able to distinguish between the intrinsic structure of this object from results that are from random fluctuations. And these two problems turn us to the study of random topology. You want to study this object from a topological perspective, and this object is random in nature. So today, I'm going to say a few words about random topology. And after that, I will have a more precise statement of a description of the preferential attachment mechanism. And finally, I'll share with you my recent result on the topology of preferential attachment graphs. Any question at this point? Is my audio going through clearly? Good.
Yeah, sounds great.
Thank you. So if you have any question, just yell at me whenever you want. Just feel free to unmute yourself. I'm very bad at monitoring the chat. And so please, if you have a question, just ask me. Okay. So random topology. In traditional topological data analysis setting, we start with a bunch of points. In this case, these are points that are sampled from a circle. And then we build simplicial complexes, and then we draw persistence diagrams and say, there's like one point that's far away from the diagonal, and so this thing is something like a circle. And these points are just too near to the diagonal, and we don't care about them. So underlying this pipeline is the philosophy that size is signal. Whatever that's big is important. So this circle is big, it is important, it's global, so we care about them. But sometimes not every signal is big and not every small thing is noise. For example, if you look at this picture, there are two squares. You should not need a PhD to see that there are two squares. So one here, the other one is here. But if you do a PhD and plot a persistence diagram, you see there's one big hole, which corresponds to this one big square. And there's this tiny thing that you tend to like dismissed as noise. So you say there's one square, and that's not good. And the reason we get this conclusion is that the small square is just too small for it to show up in the persistence diagram. And this example begs the question whether we should think of signal as size. Should we equate the two? And as a probabilist, one message I'm trying to push is that instead of thinking of size, we should think of surprise. What I mean by that is that when you look at this picture, we see two square, not because they're big or small, but because they behave very differently from random points. If you sprinkle salt on the table, you're not likely to see points that fall on the edge of two squares and they refuse to fill in the center. If you sprinkle salt on the table, it's just going to cover the plane like in a somewhat uniform manner. So we see there are two squares because this pattern is surprising. It's surprising because random points do not do that. So in short, signal is what is not random. Signal is the deviation from the behavior of random points. Now, but if you subscribe to this philosophy, you have to ask yourself what is random? How do random points behave? Otherwise, you cannot distinguish behavior that's different from random points. And this is why when we do data analysis, we should pay attention to random models and the topology. So the field of random topology has been developing for quite a while now, and there has been quite some classical results. And today I'm going to sample a few more classical results just to give you a flavor of how these objects behave. And then I'll move on to the object of interest, which is preferential attachment graph, after surveying these examples. Okay. So first of all, one of the most classical random object is the Erdős-Renyi graph. And it's constructed as follows. So you start with a bunch of points, and for every pair of points, you flip a coin, and you decide whether there's an edge between them. So let's say that for this pair of edges, for this pair of nodes, the result is head, so you add an edge. And then for this pair of points, you flip a coin, the result is tail, you do not add an edge. And you do this for every single pair of nodes, and you get something like this. So classical results that date all the way back to Erdős and Renyi in the 60s tells us that there's a critical threshold of connection probability, above which the graph is going to be connected with high probability. And below it, the graph is going to have many connected components. And the magical threshold is log n over n. But for simplicity, for the rest of the talk, I'm going to drop all the log terms because the formulae we are going to show will become increasingly complicated if we keep track of the log terms. And I'll just keep the polynomial terms. So log n over n becomes 1 over n. Now, as topologists, we don't have to start with graphs. We can look at the Clique complex by filling in all the pairwise connected subsets of nodes. So every pairwise connected set of 3 nodes, we add a triangle. Every 4 pairwise connected nodes, we add a tetrahedron, so on and so forth. And you get the Erdős-Renyi Clique complex, and then you can compute the Betti numbers. So if you run the simulation, you see the Betti numbers rises and falls as you increase the connection probability. So the purple curve captures what we've seen in the classical theorem. For low connection probability, there will be many connected components, but beyond some threshold, it's going to die down. But if you compute the higher Betti numbers, you see this pattern repeats itself at different connection probability regimes. When the number of connected components dies down, the number of cycles start to pick up, and it peaks and falls. And when it falls, the number of two-dimensional cycles starts to peak, and so on and so forth. And you can capture this by theoretical statements as well. So beyond this classical result, McHale proved in a number of papers that for each dimension in homology, there's a range of connection probability over which the homology of that dimension dominates. So for one dimension, this is the region where the first Betti number is going to be non-zero with high probability, and outside of this range is going to be zero with high probability. The intuition is that when the connection probability is too high, your holes start to get filled, and when the connection probability is too small, the holes cannot form, and so you cannot form those cycles. Okay, so this is some classical results on the Erdős-Renyi clique complexes. Any question at this stage? If no, let's move on to the other random object, which is relevant in many topological data analysis applications, which is geometric complexes. So if you pick a random number of points and you sample this number of points from an IID distribution, from a distribution in an IID fashion, you get these points. And then you can build the Rips complex and Clique complex. And then we can ask what the topology of these complexes is going to be like. And you can compute the expected Betti numbers. This is done by McHale in 2011. And it turns out the behavior of the expected Betti number depends on two factors. First, number of points, which is not too surprising. The more points you have, the more likely you can have cycles. And there's another magical quantity that captures roughly the number of points nearby. Okay. You can formalize it by considering this quantity omega, which is the connection radius raised to the dimension d times number of points. So basically, it tells you the expected number of points in a small ball. And depending on where the radius, how large the connection radius is, and depending on whether you have many points nearby, the complex exhibit different behaviors in the dense regimes and the sparse regimes. So when you tend to have many points nearby, you're in the dense regime, and your expected Betti number is going to converge to zero because the exponential term is going to dominate. And this is not so surprising because when you have sufficient connection, you start to approximate the underlying Euclidean space, which has no interesting topology. Now, when you're in the sparse regime, interesting things start to happen. And you can derive the asymptotics for different complexes. And since it's different for the Rips and Clique complex, I'll focus on the Clique complex. Okay, so this is the asymptotics for the Clique complex. And it turns out that the sparse regime can be further divided into different regimes because there's a competition between the omega term and the n term. Okay. So I've changed the scale of the line of connection radius. So now we're just looking at the sparse regime. So if you are in the sparse regime but not too sparse, meaning that the radius is in this region, then the n term is going to dominate, and the expected Betti number is going to converge to it's going to diverge. But if you're very sparse, then the omega term is going to dominate, and your expected Betti number is going to converge to zero. So we have pretty good description of the expected Betti numbers of the Clique complex. We have not just the expected Betti numbers, actually. We can also have like limit theorems, but I'll not go into the details today. But if you're interested in the persistence diagrams, we have a lot of results on persistence of cycles as well. For example, you can consider the maximally persistent cycle. So if you just sprinkle salt on a piece of on table, how likely that you have a very persistent cycle. And this work by Borowski, Kale, and Skraba says that the maximum persistence is going to have this asymptotic of log n over log n raised to 1 over k. And the idea is that if you see any cycle that's much larger than this, it's less likely to be due to randomness. It's more likely to be something else. And if you have seen almost recent work on universal distribution on multiplicative persistence, this is not exactly the same, but it is one of the early work that's have a similar flavor about keeping track of persistence of different points and how large they're going to be in a random setting. Okay, so this is so much for geometric complexes. And okay. And the last random objects that I'm gonna briefly introduce before showing you the main dish today is the percolation model. So you start with a grid and you connect nearby points with these edges. And then for each edge, you flip a coin and decide whether the edge is in the random shape. Okay. And so you get something like this. So classical statistical mechanics result tells us that there's a critical threshold probability, 1/2, above which that there's going to be an infinite cluster in the percolation. And below that, you have many tiny little clusters in your percolation. But as topologists, you can change the terminology a little bit and think about giant components. It's exactly the same thing, just different terminology. But once you change this perspective, you can start asking whether there are giant cycles in your percolation. It turns out to be slightly difficult to define giant cycles because cycles by definition have finitely many vertices. And so you cannot play the same game by considering infinite cycles. But what you can do is that you can consider a very large torus, and you can ask whether your percolation contains the cycle of the underlying torus. So for example, in this percolation, you can try to see whether there is a cycle of the underlying torus. And I'll pause a little bit for people who want to think about it on their own. Okay, I'll reveal the answer in 5 seconds. Okay, the answer is no. The reason is that if you cut out this edge and if you cut out this bit, then the percolation will deformation retract back to your point as the remainder of the torus does. So this percolation doesn't contain a cycle, contain a giant cycle. And you can ask whether this is going to be typical behavior. And this theorem by Duncan, Kale, and Schweinart says that again, there's a critical threshold at different dimensions as well. Above the critical dimension 1/2, you are going to have all the giant cycle asymptotically almost surely. And below that, you're going to have no giant cycles. So again, we have some extension of classical results on phase transition for these percolation. Okay, so I have talked about 3 different random objects, and I hope that gives you some flavor of how random topology is like and what kind of results you can get when you study random objects. Now, let's go back to preferential attachment. Since we have so many different random objects that we studied and we know so much about the topology, why do we care about yet another random model? Well, one reason is that many models that I've just mentioned are independent and identically distributed. Everything is homogeneous. But in the real world, many things are not homogeneous. For example, if you look at the internet, it's not very likely to be homogeneous. Like the Google server and my personal homepage are probably very different web pages, and it's hard to imagine that the 2 web pages are somewhat similar. Okay. So that gives us one reason to study some non-homogeneous model, and the preferential attachment graph is such case. So I will now start to define the preferential attachment model. But before that, let me get a sip of water. Okay, so the preferential attachment model was proposed by Albert and Barabasi back in 1999. And the idea is to capture the dynamics of growing networks that start to become scale-free in the sense that they start to develop like giant hubs. Now, in order to define the model, I'll content myself with a much simpler cartoon, with much fewer nodes. Okay. So in a preferential attachment model, you start with a graph where here I draw nodes as people, and these people talk to each other, and this is represented by the edges. And you add people into the graph. These people are more likely to make friends with already popular people. And the formal way to capture that is to say that the probability of that attachment is proportional to the degree of the nodes. Okay, so this blue person is connected to 4 other nodes, so the degree is 4. And to allow ourselves some flexibility in our choice of model, we'll add a tuning parameter delta, so that with a one parameter family of models instead of just one single model. Okay. And we add the person into the graph, and we update the model, update the graph, and update the degree. And then we add more and more people into the graph. Since all of them want to talk to the already popular people, the popular people will become ever more popular. So this is known as the rich get richer effect. So, and this is how giant hubs arises in this preferential attachment model. Okay. So, any question about the model before we move on? If no, okay. No. So what do we know about the preferential attachment model? We know quite a lot since it's a model that been proposed for 20 years now. For example, we know how to count triangles in these graphs. There are slightly different ways to write down a model formally, and for different models, we can have a pretty good asymptotics of the expected number of triangles, for example. And if you are familiar with the network science literature, you may have heard of the term clustering coefficient, which is basically the number of triangles out of the number of all possible triangles. And since we know how to count triangles, we have some results about these clustering coefficients as well. And there's nothing that stops us as triangles. You can actually count arbitrary subgraphs. For example, if you want to count tetrahedra, we can count that too. We have the asymptotics of the expected number of tetrahedra and any small subgraphs. We know a lot more, but these are the results that will be more relevant to us in this talk. Okay. But since we're topologists, we will not just think about graphs, and instead we'll consider the clique complex of this graph and study its topology. And this brings us to our result on the topology of preferential attachment. This is joint work with my supervisor, Professor Samuelitsky, my co-supervisor, Christina Yu, and my undergraduate mentee, Rongbi He. So our result concerns the expected Betti number, the simplest topological invariant, and the simplest statistical moment. And before we state the result, let's look at some simulation. So what you're looking at is the evolution of the Betti numbers of many different preferential attachment graphs with the same parameters. So each curve is the evolution of one preferential attachment graph. The difference between different curves is simply that we use different random seeds. Okay, so everything else is the same. The x-axis is the number of nodes of this graph. So as time goes on, you add more and more nodes to the graph, and the topology of the graph changes. The y-axis is the second Betti number of the clique complex of the graph. Okay. So it traces the evolution of second Betti number as you increase the number of nodes. There are a number of observations that we can make here. First of all, the trend is generally increasing. So that's the first surprising thing, because for the simulations we have seen before, the Betti number tends to increases as you increase connection probability, and it falls down because the holes start to get filled. It does not happen here. The trend is generally increasing. The reason is that when you add more and more nodes, cycles of different dimensions form. And so when cycles of higher dimensions form, they do fill up lower dimensional holes, but they form at a rate that's much slower than the lower dimensional cycles. So even though they form, they cannot outcompete the lower dimensional cycles. So the Betti number generally increases over time. So that's the first surprising observation. The other observation is that the growth is somewhat concave. So this is not too surprising because if you work out the asymptotics of the number of triangles, that too is concave. So, and since you need the triangles to form second dimensional cycles, it's not too surprising that the growth is not too fast. In particular, it's concave. Finally, there is an outlier in the simulation. So this curve shoots up way higher than all the other trials, and this too is not too surprising because preferential attachment mechanism is known to produce outliers because they have heavy-tailed phenomena. So you have like giant hubs, which in a sense are outliers, and again in the Betti number. In the sense of Betti numbers, we also see these outliers. So this is the simulation result, and our theoretical result corroborates with these observations as well. So we proved that the expected second Betti number is bounded between constant multiples of the number of nodes raised to some sublinear power. So it's between 0 and 1. And the power depends on the preferential attachment strength. So the stronger the power, the stronger the preferential attachment strength, the larger the power it will be. And since there's a sublinear power, the growth is concave. And this statement begs the question of what happens when this exponent is negative. So the theorem only says that the expected Betti number is going to be bounded. In particular, it's not likely to converge to 0. And finally, there's nothing special about the dimension 2. So if you replace all the instances of 2 with the dimension, and you replace 4 by 2 times the dimension, you get exactly the same result. So there's nothing special about dimension 2. The higher dimensional case is all the same. Now I will give people a few more seconds to stare at the slide in case they want to like ruminate the details of these estimates.
Can I ask a question?
Yes, please.
So in some of the other models, like a Erdős-Rényi or random geometric, I believe you would have these phenomenon where maybe H1 would dominate and then H2 and then H3. So do you have something like that? Does that appear here, or would you just say it's different flavor?
That's a very good question. For the preferential attachment clique complex, dimension 1 always dominates. And this is one of the difficulty of working with this complex, because if you have different dominating dimension, then you can use some more theoretic arguments to argue something. Here, the only dominating thing is dimension 1, and everything else is dominated by dimension 1. So you have to use other methods to argue how the cycles are going to form. So yep, the dominating dimension is dimension 1. Okay, if there's no other question, and I believe people have sufficient time to ruminate on the symbols, I'll move on to the more pictorial slides. So this quantitative statement has a qualitative interpretation in the following sense: as you increase the preferential attachment strength, the exponent is going to change, and so the behavior is going to change. A separate statement shows that the expected Betti number at dimension 1 is going to be unbounded for all time. In fact, it's going to grow linearly, and that's why it dominates all other dimensions. But as you increase the preferential attachment strength, at some point, the second Betti number will be unbounded in expectation. And the argument is simply that the exponent 1 minus 4x will start to become positive. And if you further increase the preferential attachment strength, the third Betti number is going to be unbounded in expectation, and so on and so forth. So when you look at the homological version of this graph, you start to discover there's an infinite number of phase transition within the traditional infinite variance regime. So I claim that I have a theorem, and I'll very quickly sketch the proof. And the main idea is that the growth of the Betti number is driven by the growth of the number of spheres. So this is a sphere with a square equator and 2 poles. And the growth of Betti numbers are basically contributed by things like this. But the annoying thing is that these spheres can be intersecting with one another in a very complicated way. For example, if you have another node that's also connected to the equator, then the Betti number increases by 1. And so they're not necessarily isolated, and that makes the counting complicated. So as you have more and more such extra nodes connected to the equator, the Betti number will grow linearly. So if you count spheres, you have problems because there are n choose 2 ways to pick the different poles, but the Betti number grows linearly. So what you should be counting is the number of these poles connected to equators as opposed to the entire sphere. And that, if you actually count that, that will give you the correct asymptotics. Now this is, of course, a very high-level sketch. There are a lot of subtleties you have to handle if you want to make this argument more precise. First of all, Betti numbers are not counts, so you need to do some homological algebra to relate the Betti numbers with count. And since now I've mentioned that these squares and these nodes connected to 4 corners of the equator is the dominating thing, but you can equally consider pentagons as opposed to squares. And the reason why squares dominate is that squares are the minimal thing that will increase the Betti numbers. And to identify squares as the minimal thing, you need to use some minimal cycle arguments. And since those arguments, as far as I know, are not phrased in terms of homological algebra, you need to rephrase them in homological algebra. And finally, you need to apply the graph counting results in the literature on a large class of subgraphs. So first, we need to count these pole connected to 4 points of the equator, and we also want to count other things like pentagons and so on to make sure they do not dominate. And since you need to apply the graph counting results on a large family of subgraphs, you do have to be systematic with your counts. Now, but if you believe that I can iron out all these subtleties, then you have the theorem that the expected Betti number is roughly the number of nodes raised to some sublinear power. Now, since the result gives us an explicit exponent, we can try to retrieve that in practice. So since we have the simulation, we can try to take average and take log on both sides. And we can see if we pick up the exponent from the slope of this curve, of this plot. So on the right, what you see is the log-log plot of the average of what you see on the left. The black curve is the Betti numbers, and the dotted curves are the log-log plot of the bounds we use in the proof. So you see the upper bound is a pretty good estimate, at least in log scale. And the lower bound is not too good, even log scale, but it will suffice for our purpose. And it kind of seems that there is a straight line that these growths are converging to. But unfortunately, that is an illusion, because if you actually plot the line with slope 1 minus 4x, you'll see these lines which have a very different slope when you compare it with the slope of the curve. So we're still very much stuck in the finite regime, and we're very far from convergence. The best we can do for the Betti numbers is 10 to the 4th nodes. For larger graphs, we run into memory issues, so we cannot simulate for large graphs. For the bounds, we can simulate for larger graphs, but still we are stuck with 10 to the 5th nodes, and convergence still hasn't happened yet. This does not contradict with our theory, because if you follow through the proof and work out the constants are 10 to the 18th and 10 to the minus 32. So it covers the whole thing. So it cannot be contradicted, but in order to see that convergence, you probably need to have to look at like much bigger graphs that we can handle as of now. Okay, so we have seen the theorem, we have seen the proof, and we have seen the simulation. So what are other interesting things we can do with this preferential attachment complex? So this result is a very simple result, is the simplest topological invariant, and we look at the simplest moment, and it's a very coarse result on the order of magnitude. So there are a lot of things we can do from this point. One question that we've been asking is whether we can say something about the homotopy of this complex. Now, it's probably very difficult to work out the homotopy properties of for the finite complex. But if we look at the infinite complex, it turns out that something simpler might happen. In particular, there are regimes where this infinite complex is going to be homotopy connected up to some dimension. And we're working on working out the precise bounds at which this happens, whether it happens at a sharp transition or it gradually changes. So this is for the topological property of the complex. You can also think about the more statistical questions of, say, parameter estimation. Can we improve our estimate so that it is precise enough that we can recover useful information just by looking at empirical data? So as of now, like this is an order of magnitude result that is not very good for like finite graphs that within our reach. Can we have better estimates? That would be one question. Another question is that can we come up with a model that's simplicial in nature? So right now I'm taking a very traditional random graph model and forcing the topology on it. But it would be nice to have a model that's simplicial in nature. We just keep on adding triangles into tetrahedra as we go, as we build the graph. That will be difficult, not just technically, but also it's an art, because like, okay, then you have to come up with a model that's like convincing and tractable at the same time. And finally, it's interesting to look at other non-homogeneous models. So this is one non-homogeneous models. There are many other non-homogeneous models. For example, there's the stochastic plot model. I think very few people have looked at it, and it'll be interesting to see how the topology behaves. So, I hope I've convinced you that random topology is cool, and preferential attachment graph has interesting topology. And there are a lot of open questions in this area, and we would like to know more about this field. So if you're interested in the details of our argument, this is a QR code to our archive paper. If you're interested in my other work, I have a previous work about finding small holes in the dataset. And this is another QR code for a 30-minute video of me talking about that work. So if you have not got sick of listening to me, feel free to go there and watch me speaking for another 30 minutes. But if you've already got sick of me, I will be happy to stop here, and I'll be happy to take questions. Thank you very much.
Thank you so much. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. All right, questions for Chunyin? Let me start with a question. Could you go back one slide, if you don't mind? Here, yes. So could you explain what you mean by homotopy connectedness of the infinite complex a little bit more? I mean, maybe it's the infinite complex that I need to wrap my hand around, just because for your finite complexes, you were saying you get more and more H1, it's unbounded. So,
yes.
So it's not going to be simply connected. So yeah, can you describe this a bit more?
I will try to draw something, and I think the Zoom. Okay, I need to stop sharing to do that. It is, well, first of all, the infinite complex is what you get by just adding infinitely many nodes. You don't stop at any time t, you just keep on going. So your infinite complex with infinitely many nodes, infinitely many edges. And okay, yes, I finally got the board. Okay, you can see the board, right?
Yes.
So the finite thing will have divergent Betti numbers, but it can happen that the infinite thing may have zero Betti numbers. And it is nothing pathological, because as long as you fill up all the holes, eventually that is fine. And if you're filling up holes at a very slow rate, your Betti number for the finite thing can still grow. So for example, I have this thing, which has Betti number, the first Betti number is 3. Sorry, it's 3, yeah, 3. Now, if for the next step, I fill them in with squares, and then I add like 4 squares, so that the Betti number will grow. And if I fill in the next step, and draw this. Okay, this is ugly, but you know what I'm doing. So the Betti number is still growing, but every single time I'm filling up all the old holes. So for the infinite thing, everything is going to be filled up. And so the infinite thing is going to be contractible. But at every single finite stage, your Betti number is still growing. So it is not pathological that the Betti number converges to infinity, but for the infinite thing, the Betti number is 0.
So your question about the infinite thing is about the homotopy connectedness, like the homotopy groups. But if you were
Yes.
asking about the homology, sort of, I guess the homology of the infinite complex is just the semi-infinite bars in persistent homology. Is that correct?
Things that, so if you look at the homology, you need to look for things that never die. So yes, that will be the semi-infinite bars. And if you have any of them, that will be an obstruction to the homotopy connectedness.
Thanks for explaining that. I appreciate it.
Thanks for the question.
More questions.
Yeah. Hi.
Hi.
Hi, Chen.
Andrew.
Yeah. So I had a question about like what's preventing you from sort of because you have, it seems like you have asymptotics for pretty precise asymptotics for the 0 and 1 dimensional homology. What's sort of preventing you from using the Euler characteristic and working backward from that?
So,
you know, because the Euler characteristic would be presumably fairly simple because you're just clique counting there.
So the Euler characteristic is going to be dominated by the first and the 0th and the first dimension, because both of them are linear.
Yeah, right. But I mean, you can, you know, is there any way you can sort of suitably, you know, account for that, and then be able to find this higher dimensional stuff by like, you know, subtracting this off of the Euler characteristic and looking at the remainder or something?
So I think for the Euler characteristic, okay, if you only look at the first term, then you get something linear subtracting something linear, and then so you will need to have the lower order terms for both for the Euler characteristic, and I'm not familiar with any results that give us the count of cliques in high dimension. Okay, we have those results, but those results are also order of magnitude results. So we do not have the lower order terms. One thing we're trying to do is to work out the precise leading constant for the higher dimensional cliques. But that is still only for the leading constant. For the lower lower order terms, it's still out of our reach at this point.
So the main impediment is just the order of the higher dimensional cliques then.
Yes, so we do not have the lower order terms of higher dimensional cliques.
Yeah. right? Which is what you would need to establish anything
Yes.
useful. Because yeah, all right, cool. Thanks.
Thanks for the question.
More questions? All right. Well, if not, thank you so much, Chunyin, for the very nice talk. And let me end the recording here.
Thank you very much for the invitation and coming.